Really understand any material, we have to start small. I mean, at the atomic level.
Okay, so let's dive in. It all kicks off with how the atoms themselves are arranged.
This concept, APF, basically tells us how tightly packed those atoms are. It's super fundamental.
And yep, this is a core concept, pulled straight from actual university exam papers. So let's solve it.
So on the left, that's the BCC structure, and on the right, you can see the calculation.
And this tells us something brilliant. The APF for this structure is 0.68, or 68% full.
All right, let's build on that. Now we'll go from pure elements to these powerful things called alloys.
Engineers use these phase diagrams kind of like recipe books to create alloys with specific properties.
Now, the most important of all of these is the iron-carbon diagram. It's a cornerstone of metallurgy. But you know, an alloy's properties aren't fixed. They can actually be transformed with heat and time.
This is a time-temperature transformation diagram, or TTT for short. It's basically a roadmap for heat treatment.
By taking different paths on this map, we get processes like martempering and austempering.
So the crucial point here is, we can design materials. Let's check out a pretty modern method.
This is powder metallurgy. It's a way you can build complex parts, not by cutting, but by joining.
It involves making a powder, pressing it into shape, and then heating it until all the particles bond.
So why does all this theory actually matter? Because, well, this knowledge engineers our entire modern world.
So let's connect this back to real materials, like industrial zinc and, high-tech lithium.
Their unique properties all come from their internal structure. That's essential for batteries, alloys, and so much more.
Understanding this science means engineers don't just get to use materials, they get to invent them.